4.5 billion years ago, our cosmic neighborhood was a shooting gallery. The young Earth was completely molten, constantly pelted by massive incoming asteroids and baking in an immense, relentless heat. That intense environment usually guarantees a barren future. Look at our immediate neighbor, Mars. Its reddish crust is entirely bone dry today, save for a small frozen polar cap. Venus swung the opposite way. It is completely locked inside dense yellowish white clouds, baking underneath as a toxic, superheated oven, incapable of sustaining liquid on its surface. Yet somehow, Earth broke the pattern. Look at this image. 71% of our planet's surface is covered by deep, liquid water. How did a planet born in a fiery, violent crucible manage to acquire and hold on to enough water to drown most of its own crust? Earth's oceans exist as a rare cosmic anomaly. This massive volume of water required a highly specific chain of events to break the dry rules of the inner solar system. Planetary scientists tracked this water to two primary delivery systems. Either it crashed down from above via ice-rich asteroids, or it bubbled up from deep inside the planet itself. Early Earth held massive amounts of steam trapped deep inside its hot mantle. Through a process called volcanic outgassing, that steam was violently expelled through the crust, filling the early atmosphere. As the rock finally began to cool, that thick atmospheric steam condensed. For millions of years, it rained, slowly pooling into the lowest basins of the newly hardened crust. Originally, there was only Panthalassa, a massive superocean surrounding Earth's early unified landmass. But the crust is restless. Shifting tectonic plates began tearing that supercontinent apart. As the land separated, the singular ocean rushed in to fill the widening gaps. The seas we navigate today are dynamic. They are active basins, constantly carved and reshaped by the mechanical fracturing of the planet's surface. That ongoing tectonic division gave us the modern configuration of 5 distinct oceans, each executing a highly specific role in the global machine. This map highlights the vast, deep Pacific Basin, completely ringed by a volatile perimeter of active volcanoes and fault lines. Moving to the Atlantic, the floor actively expands. The mid-ocean ridge creates new crust, pushing adjacent continents further apart. Then there is the Indian Ocean. Its surface waters absorb massive amounts of heat, turning it into a thermal engine that drives chaotic global weather and massive monsoon systems. At the absolute ends of the Earth, the southern and Arctic oceans freeze over. These freezing extremes act as a global pump, driving the deep water currents that circulate below. When we stand on the shoreline, the surface often looks incredibly calm, hiding the immense geological and thermal forces grinding away out of sight. We have drawn borders on maps and given them 5 names, but they act as one interconnected, highly specialized global engine. Understanding how this engine was built is one thing, but right now, today, it is actively preventing Earth from reverting back to a dead rock. Phytoplankton drive the ocean's biological heavy lifting. These are diatoms, a specific type of phytoplankton. Notice their highly complex geometric cell structures. They are entirely invisible to the naked eye, but they exist in the trillions. Through photosynthesis, these microscopic, ocean-dwelling organisms produce the vast majority of the oxygen required for every terrestrial creature on Earth to breathe. They are the actual lungs of the planet. Beyond making the air breathable, the ocean acts as a massive thermal sponge. It absorbs dangerous levels of incoming solar radiation, stabilizing the atmosphere and preventing it from superheating. Powerful global currents then take that absorbed equatorial heat and violently distribute it outward, pushing the energy all the way to the freezing poles. By regulating both the air and the climate, these ancient active forces maintain the narrow window of habitability